So, well, we have talked about band gaps, we have talked about electron holes in a semiconductor. So now we will go back to the original, the first question, the classification between metal semiconductors and insulators. At that time, we simply said the conductivity is such and such number. Okay? But now we are in a position to actually go a little bit more. We can provide a deeper explanation to that. So if you look at an insulator, it turns out that an insulator is basically a material whose valence and the conduction bands are separated by a large energy band gap. Because when we did all these bands and all that, we never really took the type of atom, right? Any atom can have a band, provided it has a crystalline structure. So, so a glass also has some sort of, it can form an amorphous and also quartz, which is crystalline form of glass, and diamond, of course, it can be a crystal. So when you have these things, you have a large band gap. So the band gaps are shown in the figure here. This is about 9 eV for glass and 5.5 eV for diamond. So when you have these large band gaps, then we already saw the difficulty in producing electron hole pairs. So what happens? Simply you're, depending, of course, you have to look at the periodic table and elements and all that. But it turns out that this band will be full. This band is the conduction valence band is full, conduction band is empty. There is no possibility of generating electron hole pairs, so they cannot conduct. Larger the band gap, the better insulator it is. Okay. So why is the band gap large? I'll leave it to you right now. I mean, think about it. It's not hard. You can apply the analysis from particle in a box and analyze it. Okay. All right. Then what are semiconductors? Semiconductors are those materials which have intermediate band gap, is what we said, right? So here are a few numbers. Energy, the band gap for silicon is 1.12 eV. Band gap for germanium is 0.66 eV, and band gap for gallium arsenide is 1.42 eV. These are calculated using numerical approaches. Okay, why these numbers? I mean, it becomes difficult to analyze without intuitively. But you could still think about just compare silicon and germanium. Okay, they have the same lattice type, lattice type, diamond lattice, right? Diamond cubic lattice. So go back and look at lattice constants of these two materials. Just type Wikipedia, search for germanium. It will show you, the Wikipedia page shows you the lattice type. Same for silicon, so you can analyze. Try to see if the lattice constant is somehow related to band gap. And if you apply the same analysis to gallium arsenide, it won't work. The reason is it has a different lattice type. All right. So this is not possible. Well, anyway, you take a look. And by the way, the temperature plays a major role in band gap. We never really considered that. In our intuitive picture, we simply said this bonds, because they have these bands happening, and then the bands will interact and form the energy levels will interact and form bands. Why, why should the band gap be dependent on temperature? That's an interesting question. If you think about it, what happens when you increase the temperature? You're transferring energy to the lattice, right? As you increase the energy, what happens to the lattice? The material expands, right? When the material expands, it's actually the lattice which is expanding. So lattice constant is increasing. Whenever lattice constant increases, what happens to band gap? Go and think about it from the particle in a box analogy. Whenever your size of the box is large, the spacing between the energy levels reduces, right? And after all your bands are originating from those discrete energies in the particle in a box, right? So from that, you can understand that the band gap should lower. So there is an empirical relation usually given for each semiconductor, how much it changes with temperature. It is not necessary for us in this course. It's a little bit more of a detail, but it's enough if you understand that temperature has has an impact on the band gap. All right. The last class of materials are basically metals. So what happens in metals? Well, it turns out that the band gap is very small. Okay. And if the band gap is very small, electrons can easily jump into the conduction band. And if they do that, they're available for conduction. And that is why the conductivity of metals is large. This is one scenario. Some of the metals might actually have even more extreme case, wherein the bottom of conduction band of CB is actually below the top of BB. Okay. So if this happens, then because of this overlap of bands, lots of electrons are present in the conduction band and they can conduct. Okay. So because of that, metals are very, very good conductors of electricity. All right. Okay. So there is also another interesting aspect that you can understand. I don't know if you have thought about it, but well, yeah. If you, how does a piece of silicon look like? Now, this is what are called as these are what are called as silicon wafers. These are essentially about 525 micron thick, half a millimeter thick wafers. I mean, that's a typical number. It could even be 750 microns in the latest technology. But anyway, so 525 about 8-inch wafer. This was used in the past. Nowadays we use 750 micrometer thick and then 12-inch. So these are the wafers. So this is basically a very, very smooth. If you look at the surface, it's shiny. It is shiny because it's atomically smooth. If you measure the roughness, it's going to be 0.1, 0.2 nanometers. It's very, very smooth surface. And that is silicon. Okay, you have this perfect pure material of silicon, which is fabricated into these wafers. You could also do similar thing for glass. So glass is silicon dioxide. But if you look at it, glass is transparent. I mean, we see that every day. Silicon doesn't look it is like it's transparent. Why is this difference coming from? Okay. The difference, it turns out, it comes from the band gap. Glass has 9 eV band gap. When you have a 9 eV band gap, and we saw that if you take a visible light photon, we'll take the smallest wavelength so that you have the highest energy. The smallest wavelength is 300 nanometers, let's say, in the visible range. Okay. The corresponding energy is basically, I think, if you do 1.24 divided by 0.3, so multiply by 3, so it will be about 3.7 something. Let's take it as 3.7 eV. Okay. So when you have this photon incident, can it make an electron jump from the valence band into the conduction band? Well, it turns out that this cannot happen. The reason is there is no state available at that energy. The band gap is 9 eV. So there is no state available at 3 eV or so. So we cannot make this transition happen. So the photon goes through glass. Whereas if you look at silicon, the same photon, silicon has a band gap of 1.12 eV. So when you shine a photon, the similar energy 3.7 eV photon, then of course electron will jump into the conduction band, and that's why you have EHP generation, and because of that the photon gets absorbed or annihilated. Okay, and you have these electrons which are flowing, and this is a very, very important process. If you think about a solar cell, what happens in a solar cell? Well, you have light shining. When light shines, it's creating electron hole pairs, and those electron hole pairs will move. There's a little bit more to it, but we will talk about it in the last 2 weeks of the lecture. But then how a photon interacts with a semiconductor is a very, very important part of optoelectronics, LEDs, lasers, solar cells, and so on. All right. Okay, we will look at it later. Right. The last thing I want to do today is talk about direct and indirect bandgap semiconductors. Okay. So this is a EK diagram for gallium arsenide. Okay. It's more complicated than what you saw with the chronic penny model. The reason is that it has additional, it's actually showing you the EK diagram in 2 different directions in the same plot. Okay. So this, just accept it right now. This basically is one direction. You could say this is one direction in the lattice, and this is another direction in the lattice. Okay. These 100, 100, and 111 are Miller indices, but we said that we would not want to go into the details. We just are showing you all the all the major directions. They're showing you in a single picture. That's all you have to remember. Okay. So now what it is showing you is that you don't have that simple parabola, right? If we took a chronic penny model also, it would have been a parabola, some sort of a parabola, right? It was, but now it turns out that it has a little bit more complicated shape, and why that happens? It's done because of there's a lot more theory behind it. And these are calculated using what's called as density functional theory and all that, which is not important for us. Okay. So the only thing I want you to focus is that there are two bands. One is the valence band, which is basically in this way, and the conduction band, which is on the top, separated by a band gap. Okay. Usually, the top of the valence band is denoted by energy equal to zero here. Just for reference, I mean, it doesn't really matter. Okay. So now, the band gap of gallium arsenide is 1.42 eV, and that is what is shown here. This distance Eg is 1.42 eV. And now, and another small thing to note for the future is bands are parabolic, parabolic near extrema. Okay, we will use that fact later on. Okay, so now you have this. Why do we call gallium arsenide a direct bandgap semiconductor? We call it a direct bandgap semiconductor because this is bottom of conduction band and it coincides with top of valence band. I mean, they occur at same K basically. Okay, this is important. So whenever this happens, we call it a direct band gap. Okay. Now we have to look at one more step in this. We have to look at energy conservation, because what happens is if you shine a photon on the direct bandgap semiconductor, what happens? Let's try to write out the energy conservation law. Okay, conservation. Energy, conservation of energy. Okay, what do we do in this? Let's say there was an electron at the top of the valence band. Okay, so that will be E initial. Okay, and you are shining a photon. You are giving an energy to the electron, right? So I'll say, I'll put a subscript E just to denote that it's electron, and then you're supplying energy to it. So that is h nu. When you do that, you have to make sure that the energy is basically E final. So this will be, in the valence band, in the conduction band, right? The top energy has to be in the conduction band. You might ask, why doesn't energy, from below the, if why not an electron go from this point to this point? Right? That becomes more complicated. It does happen in some certain situations, but let us not worry about it right now. Okay? So this is the energy conservation. You can write it like this, right? Simple. So what this tells you is that what is the bottom of the conduction band? This is basically EC, right? And the top of the valence band is, I'll put it this way. This is EV, okay? And so this turns out to be h nu, okay? Basically, h nu is equal to Eg. Whenever this happens, you have the absorption taking place. The conservation of energy is satisfied. But if you have a photon of a lower energy, then there is no state available here. It cannot get absorbed. Okay. So this is again the same story, repeated in a different way. All right. So this is direct bandgap semiconductor. In addition to this, we have what are known as indirect bandgap semiconductors. In an indirect bandgap semiconductor, you have the EK diagram, which looks slightly different. In this case, the top of the maximum of valence band does not coincide with bottom of conduction band. Okay. This implies we call this, whenever this happens, we call it an indirect band gap semiconductor. So we see semiconductor. Okay. So, but still the energy is the same thing. The band gap is always defined as the energy gap between the top of the valence band and the bottom of the conduction band. That story is still the same, but the position at which this occurs is different, and because of which there is basically this difference. What essentially it means that there is a difference in the momentum. There's a difference in the momentum. So we know from our classical physics there are two conservation laws. One is conservation of energy and the other one is conservation of momentum. So will the conservation of momentum be satisfied? Conservation of momentum. What happens to it? If it is satisfied or not. If it is not satisfied, the transition is not likely to happen. So how do we write conservation of momentum? We have to write basically, we can refer to K as a momentum, okay? H cross K, P equal to H cross K, we saw that, right? So we will say K, we'll just write in terms of K, you can always multiply by H cross. So basically, it's up to us, let's say Ki, okay, initial momentum of the electron, okay, plus momentum of the photon, K photon, should be equal to K final of the electron. Now, from the indirect band gap semiconductor, we are seeing that the initial momentum, let's say the electron was at the top of the valence band, and in this diagram it is shown as K equal to 0. So let's say this was 0, right? And K final, let us say this is K, I don't know, K naught we'll call it, okay, just for reference, okay. So the bottom of the conduction, or KCB we'll call it, okay, KCB. KCB means basically the momentum at which the minimum of the conduction band occurs. So this is KCB. Now, will this relation be satisfied or not? Okay, how do we decide that? To decide that, we have to know what is the momentum of the photon. What is the momentum of photon, right? Momentum is m times v, right? Mass into velocity. And we have all studied that photon is a massless particle. So momentum is 0. Well, that's not exactly accurate because photon is a relativistic particle. And whenever you have a relativistic particle, you have to use a different expression for calculating momentum. So the momentum of a photon will be given by P equal to h by lambda. Okay, and lambda is a little bit inconvenient for us when we deal with semiconductors. So we will write it in terms of energies. So we know that energy is hc by lambda, right? And because of that, you can substitute P here. So basically, this will lead to E equal to Pc. This is the momentum of a photon. Okay. So if you calculate this, you could easily do that, right? So if I take, like, for example, I'll take a 1 eV photon. 1 eV photon. What is its momentum? Implies P equal to 1 eV divided by C, right? But 1 eV I can't use. I have to, EV is just a convenient unit for us. It's not a physical unit. So I'll say I have to multiply by charge. So EV, I have to, 1 EV is basically how much? 1.602 into 10 power minus 19 joules, right? 19 joules divided by the speed is basically 3 into 10 power 8. So this will give you approximately, I think, 5.4 into 10 power minus 28 kg meters per second. Okay. Just check it out, but I think this is right. Okay. So this is your momentum of the photon. Okay. So, but what is the momentum of the electron? Typical momentum. Let's say this energy is 1 eV. Okay. So 1 eV electron's momentum will be implies, how do you calculate momentum of an electron? You could use de Broglie relation, or we have energy. So basically, E is equal to, remember the dispersion relation, E is equal to P square by 2m, right? You might say, oh, well, this is not exactly a free electron. Well, yeah, we understand that, but we want to get a rough magnitude. Okay. So basically, P will be root of 2me. And if you calculate this, I believe it turns out to be 5.4 into 10 power minus 25 kg per meters per second. Just check it out again. Okay. These numbers, there is always, I have just done it before this, so I should be right, but you can verify. So what is the conclusion? Okay. The conclusion is that momentum of a electron is much, much greater than momentum of a P of a photon. Okay. Or rather, since we use K in the top, let's say K electron is much, much larger than the K photon. That means if you have an indirect band gap semiconductor. So I mean, I can also, in other words, I'll also say that momentum of photon is negligible. Okay, when I say this, I mean negligible in comparison to electrons. So sometimes k equal to a photon has a zero momentum, I'll say. Okay, that's just a colloquial. I mean, that's a very shorthand way of saying that. Okay, it has negligible momentum compared to the electron. Okay, so when you have photon momentum to be very small, can this relation be satisfied? This relation, right? Let me put this in. This is what conservation of momentum is, right? Can this be satisfied? No, it cannot by itself. Okay. So, optical absorption process in a indirect bandgap semiconductor is less efficient. Optical absorption in indirect BG, let's short form here because I don't have space. Indirect bandgap is less efficient. If you write out the same conservation rule for a direct bandgap semiconductor, you saw that the K minimum and the K initial and K final were at the same K. So negligible momentum of photon was actually good. I mean, the conservation law was satisfied. So direct bandgap semiconductors are efficient light absorbers or even emitters. That's why whenever you see lasers and LEDs and all that, they're all made of direct bandgap semiconductor materials. And that's why most of them are usually in 3-5 materials, which have direct band gaps. Whereas indirect bandgap materials are not very efficient. I mean, there are ways to beat around that. There is a lot of latest research which tries to work around it. But even today, we don't really have a silicon laser. We have a laser sort of gallium arsenide, indium phosphide, and stuff like that. But we don't have out of silicon. Okay, that is the reason for this. All right. So, can an absorption occur at all? Yeah, I only said it is. I didn't say that it's not possible. Generally, if you have a conservation law which is violated, you would say that it is not possible. But I'm only saying that it is less efficient. The reason is that you can have a what is called as a second order process. Okay, so if you shine a photon here on an indirect bandgap semiconductor, let's say I shine a photon of energy equal to bandgap, then this electron can go only here because photon has no momentum, right? It cannot change k. It only can make a vertical transition in the EK diagram, not a horizontal transition. Okay, so a photon can make this happen, and then for actually the electron to go into the final state, it requires help from a different type of particle which we call as a phonon. A phonon is simply a unit of lattice vibration. Nothing, let's not get into that. Okay. So it requires an additional quasi-particle called as phonon. So a combination of these two can actually make a transition occur. So if these two occur simultaneously, then you can have transition possible. Okay. So the conservation law will be satisfied. Of course, you have to rewrite this conservation. You have to put a photon momentum also. You have to write a vector sum of that. Okay. But anyway, it's not necessary right now. All that. Okay. So it's just that the second order process we call it, and that is less efficient. That's why indirect bandgap semiconductors are not good light absorbing or emitting materials. Okay. So and typically, most of the popular semiconductors are all indirect bandgap, unfortunately. Okay. So this is silicon. Right? Silicon is an indirect bandgap semiconductor. So is germanium. You might ask, then why is silicon the most? It looks like it's less efficient. So why is it the most popular semiconductor? Well, it turns out that it is actually cheaper to make. It's more widely available. Gallium arsenide is much more expensive. Okay. So, but it still works for us. Silicon works. That's enough. Of course, gallium arsenide has better properties in some senses. So there are electronics made out of gallium arsenides and other graphite semiconductors, but those are more expensive and they're useful for specialized applications. Okay. For routine applications, we use silicon. All right. So this is where I would like to stop. Today we just talked about various electrons and holes in semiconductors. We talked about how electron in a conduction band, what does it mean? A hole in the valence band, what does it mean physically? And then what does it mean on the band gap? We talked about that. And then we talked about various processes to produce electron hole pairs in semiconductors. And then finally we talked about indirect and direct bandgap semiconductors. With that, I would like to stop for now. We'll continue in the next lecture. But I also just wanted to make a small announcement that I'll be recording a short demo of the wave functions in infinite and finite potential wells. So we talked about it in the last two lectures. I said that we have taken some wave functions from the software. We just used a library that was created by somebody else, and then we just adapted it to show you, those graphs. So I'll be actually posting those things directly on the GitHub. You can download it and you can try it out. So this is not, not necessary for BTechs, undergraduate students. But if some of you are, postgraduate or research level students, I would encourage you to actually go and take a look at the code. It's fairly simple. It actually, deals with finite, infinite, potential barriers, wells, chronic many model. All of it is dealt with in the code. Okay, you don't have to, it will be a good experience for you if some of you are interested in research in semiconductor devices, and also you're interested in coding. So it will be a nice idea to actually go and take a look. You'll also understand a little bit about how to solve differential equations numerically. These are all essential skills. As an internship project, maybe some of you are interested and you can do that. Okay. But anyway, if you are interested, you can approach me separately. For now, I just show you the interface and how it looks, and I'll just post the necessary things on GitHub. All right. So thank you very much. Let's stop here. I look forward to seeing you in the next lecture.